And that should complete the things that you should be able to do also at the exam. Last week, I more or less got stuck over there. So factor analysis, we have a large item battery, all kinds of questions measuring more or less the same thing. That's at least the idea. And we had happiness as an example. And in fact, we used our own data as well to try to understand how this works. These are the three things that we needed to go through, and we did two of those. Actually, the most complicated one we already did. That's the rotation part. So what we need is three steps. First, we want to figure out how many dimensions are in that set of items, and we hope as few as possible, perhaps one. And if we're unlucky, then, well, perhaps two or three. And if we are really unlucky, then it's not possible to reduce the data to fewer than the number of items that you had. If that does work, let's say you extract here and you find, let's say, 2 dimensions. Actually, more likely, you'll find something like might be 2, might be 3, perhaps 4. Then you rotate. You try to figure out, okay, if there would be 2 dimensions, what would they be? And, well, this is sort of a tedious process. As soon as you find out, okay, I've got a pretty good idea here exactly what it is. Could you get rid of the phones, guys? You too? So now we know we have 2 dimensions here. We have an idea. What do these dimensions represent? And now we want to create the new variables in the data that we're going to work with. So we start with for the, what was it? The big 5. We have 40 or so items. It's supposed to be 5 dimensions. So in the end, we need 5 new variables in there representing these 5 dimensions that we are hoping to create here. So here I have a note for me to show you just briefly what we had before. We had a very easy example in the sense that everything worked out rather well. We looked at the questions Q9. That was all about the extent to which you gather all the necessary information before you decide and these kind of things. Let's see. We had a factor analysis there and the scree plot. In the end, 2 dimensions. Let me just show you this up to here. This we had before. And here we saw, well, this is how you want it. We have 5 items here neatly lined up together with high weights on dimension number 1. And the 5 other ones that we have high weights on factor number 2. And all the things that we could have here that we do not want, for instance, that there are high values also over here, so that a single item is loading on 2 dimensions. You don't want that. It's not happening here. Or that we have, let's say, too many where you do not see 0.8s and 0.9s, but also 0.4s and 0.5s, also something that you do not like so much. Well, all that worked out well. So this is the first factor. That is the second factor. And now we continue to try to figure out, okay, if we believe that this is it, the first 5 items, that is something, and the second set of 5 items, that is something. Now, how are we going to calculate the new variables in the data? And I'll keep it like this instead of full screen because it's easier to switch back and forth. Here you see that there are 3 ways to do it. And if you're lucky, it doesn't make a difference. But nevertheless, we need to know what the differences are. So the first one, here denoted as A, is the easiest thing right after a factor analysis. You simply type that Stata needs to predict the new values, and then it will create the new dimensions. I'll show you how that works in a minute. So you do your factor analysis, you rotate, you look at your data and you think, okay, this is the right one. Now you ask, predict the new dimensions in my data. That's one way to do it. The other thing would be, well, you could just calculate a scale score value per dimension. So if we have 10 items, as we have here, we see the first 5 are supposed to fit on 1 dimension. Okay, forget about factor analysis for a minute, and just run a Cronbach's alpha on these 5 items. What you're going to get is the mean score. So what you are going to get by definition is that all these different items are going to get the same weight, but might be good enough. And here, when we saw that in that table, it's all 0.8, 0.7, and so on. So these weights are more or less similar anyhow. So that might not be so bad. And you run this alpha command twice. once on the first 5 items, once on the second 5 items, and then that's pretty much it. Could you get rid of the phone as well, right there? Thank you. The third way to do it would be, well, if we now know that the 10 items can be divided in these 5 and those 5, what we could do is run our factor analysis again, but now on just these 5. If this is supposed to be one dimension, and if I then run a factor analysis on these 5, what I should find is, well, this is one dimension, and I then simply run a factor analysis on that. This will allow that the weights for these separate items are different. So not equal, as in the B option, but slightly different, as it was also possible in the A option. Okay, so there are advantages and disadvantages for all of these. First, it's perhaps easiest to see in the Stata example. This might be a bit misleading because it looks like we have zeros over there, but you don't have zeros actually. It's just that we have gotten rid of all the values below 0.3. So actually this is the same table, but now with all these values below 0.3 included. And what you see is now, well, if you allow Stata to calculate that first factor, then you will see here that all these, the first 5, will get relatively large weights. And these are getting quite a bit smaller weights, but are nevertheless included. So that is suggesting, okay, even if you measure that first dimension and you feel that first dimension is totally determined basically by these first 5, nevertheless, you'll get a little bit of the last 5 in there as well. And that need not be a good thing, because if it's obvious to you that the first 5 are a set that belong together, then why would you include the other 5 there as well? In all likelihood, it won't do that much harm as long as these numbers are small, but nevertheless. Same thing for the second dimension. To a large extent, this is determined by these numbers. And these are really small, but if you feel strongly that this is a dimension, these 5 and these do not belong there, then it might be a good idea just to disregard those. And if you run an alpha command just on the first 5, then obviously you know that number 6 through 10 are simply not in there. Okay, so let's see. Yeah, here you see this typed out, but it's easier to see it in the do file, I think. Okay, so in this part over here, from A to there, I'm calculating these different kinds of predictions. So here you see this is my rotation at the end of the factor analysis. Here I thought, yeah, great, first 5 and the second set of 5, and then we're done. This is the first way to do it. This is, in a way, closest to what factor analysis by definition is. I type a predict command and 2 names here. The names you can choose yourself. These are the names of the new variables that Stata will create. And in this case, I'll call them factor 1a, the a representing that first way to do it, and factor 2a. And, well, what you would maybe want to have is something like this. I'm checking here. This is the new variable that I created. So this is its first factor. And now I run a regression analysis on all these, on the 10 items that I have. So let's see what happens there. Oh. You see here an obvious adjusted r squared of exactly 1. This is a perfect model because that new variable is created from these 10. It only allows us to see here exactly what the weights are that Stata has used behind the scenes. And you'll see here, indeed, for this factor 1 through 5, has weights that are relatively high, let's say 0.3 or so, and 6 through 10 has weights that are relatively small. So in all likelihood they won't hurt as much, even if they do not belong to the dimension. But here you can see exactly what the weights are that have been used by Stata. Then that B option, that is in principle nothing new. This is the second method scores. I run an alpha command here on the first 5, and I generate something that's called factor 1, and now with the B behind it. Or you do it on the second set of 5, and you get an alpha score as well. So let's see how that turns out. An alpha score here of 0.82, which is good, and a score here of 0.75, which is a bit less good, but nevertheless quite decent. So that's another way to do this. And the other way to do it is a bit more elaborate. If you have the feeling that, and in this case I normally wouldn't, because here, Let's see, where were we? Here you can take these numbers, not exactly as the same as the weights for these, but they are representative for these weights. So if I would have numbers here that vary quite a bit, let's say also a couple of 0.4s and 0.5s here, then it might be a good idea to think about not giving all these items the same kind of weight. But here they are so close that in all likelihood that won't happen. But nevertheless, let's see. What I now do in the do file here is I run a factor analysis on the first 5, and I double check that there is one factor. Okay, we have that parallel analysis plot, that Fa command, and you see indeed that there is one huge factor over there, and all the rest is below the dashed line. Also, if you look at the output, you'll see here there's one eigenvalue over 1, and the rest is below. So even if I use that Kaiser criterion, which says take everything above 1, then I would also say that there is one dimension. So indeed, this is working out. There is one dimension here. And what I now type is predict factor 1c. So this is factor 1, but then using method c. Do the same thing here. Okay, let's double check. This also works for that second set of 5. Oh, there you have it. Also one huge factor over there, and the second one below 1. And in this case, I want to compare here. I've now created factor 1 in 3 different ways using the A, B, and C method. And same thing here for factor 2 using that A, B, and C method. And let's see if it makes a big difference. Oh, okay. Here we see the correlations between the different ways of calculating. Well, you see this in this case, which is relatively obvious. We could see that coming a mile away. These are really the same. So factor 1a, the correlation with 1b is 0.998, which is really high. Basically the same thing for all the other ones. So in this case, it didn't make a difference at all whether or not you use A, B, or C. And in a way, this is basically what you hope. You don't want to have to think about, okay, should I predict or create my new variables using method A, B, and C, and then get totally different results. Not a nice thing. So usually you do this just to double check that it doesn't make so much of a difference. Okay. Back to this part. So here you see this once more. After your rotation, you predict, and here I have 2 dimensions. If I would have had 3, then I could have typed factor 3 there, or however many I want. You use an alpha command on the separate items. That could work, or you use a factor command on the items about which you think that they fit the dimension that you're looking for. Okay, that's it. The only issue is it's supposed to be about factor analysis, and this is not factor analysis, what I told you about. There is a difference. This, what I just showed you, is actually called principal components analysis, which is the, let's say, the twin sister of factor analysis, and there is a difference. So what is the difference? Yeah, first of all, it's a good idea to know that there are quite a few different ways to go about these 3 different steps. So in a minute, I'll complete the factor analysis part, and then we will see that there is a bit of leeway as to what to do exactly. And that bit of leeway can cause that when you try it and I try it, you might get something different than I have, even though both of us did something reasonable. And in fact, it is worse than that, because I'm not going to cover all the ways in which you can try to extract here. For instance, this is principal component analysis. That is what we just talked about, actually. Factor analysis I talk about in a minute. It's every once in a while also called principal axis factoring. That's slightly different, so might lead to a different result. Maximum likelihood extraction is possible as well. Again, slightly different. Won't talk about that at all, but it's possible too. And there are more. Okay, so trying to get the number of dimensions in your data is to a large extent also open to debate and may depend on exactly what you try here. Then we have the rotation part. Well, we have 2 that we considered. One that we didn't consider even so much, but it's variance. This is an orthogonal way of rotation that we didn't use so much just yet, but was mentioned last time. Promax is the one that we will typically use, and there are quite a few more, in fact, that we could also use. So you could, in principle, go on for ages trying to find a rotation, so let's say a different view at the data that will make you help understand what's going on. And we only looked at 2. And here, okay, there's even a little bit more down there, but we already saw that we have at least 3 different ways to calculate these variables. Okay, so what's the new idea here? Well, what we had was, in that example, 10 different items, and we want to basically rewrite the 10 into 10 other variables, and then be able to say, okay, from the 10 other variables that we have, we only need the first 1, or the first 2, or the first 3. And in that example, what we had is, well, if we rewrite the whole thing as 10 new variables, then we only need the first 2. Because in the first 2, we can put items number 1 through 5. In the second one, we can put items 6 through 10. And then we have pretty much all the variance in the original data that was there before. And the other ones, 3 to 10, are in principle there as well, but we can disregard them. That's the idea. The only thing is, well, for all these items, what you can assume is that there are at least 3 parts in there. One is the part that you are actually willing to measure here. So if it's happiness, then you think, okay, to some extent, the happiness thing that is in the person that I'm trying to measure is being measured with that item a little bit. Then there is a little bit that is about happiness, but that is related to the actual item. That specific item measures one specific aspect. I don't know how happy you are when you rise in the morning, and that might be saying something, but not completely. Perhaps you're not so much of a morning person, and in general you are happy, but it takes 20 minutes to get a head start. So that is specific to that item. And there is junk, noise, error of all kinds of reasons. I don't know, you had a bad day today, or you didn't pay much attention to the question. It could be anything. So there is noise in there as well. And what we did so far is rewrite the information that we had in the items without any special treatment of the fact that we know that there is noise in there. And what factor analysis does is it tries to get rid of the noise. Or stated differently, that what we did up to now, the principal components thing that kept the noise, it kept also all the information in there, so you're sure that the new variables basically are the same as what you had, but you also know that the noise that you had in the original ones has remained. And factor analysis takes a stab at trying to get rid of the error that you have in there. There's only one problem. The only way to find out if trying to get rid of the noise has worked is by looking at the interpretation of your dimensions. So if it's better possible to come up with a decent interpretation of your data, that is the only way to figure out that, in this case, factor analysis got rid of some error variance that works for me, because now I can understand better what my data looks like. And it would have been nice to have, I don't know, some kind of statistical rule saying, now I see that I've reduced error variance or something, but unfortunately it's not there. Okay, so let's see. Usually to try to estimate the common variance there, one way to go about it is to do this here. You take one item and you make that the target variable. So take one of these 10 items that we have and try to predict it with the other 9. We look at the R square of that, and that R square is a measure of the extent to which there is common variance in that item. If it's possible very well to predict item number 8 with all the other 9, then apparently something's in there that's also in these other 9. And that's usually taken as one approach to try to figure out how large that common variance is, and thereby to get rid of that random variance as well. Now let's see that happen. I have to see here. Yeah, this is basically the same thing, but in words. This is the important part to remember here, that factor analysis, where you do try to get rid of the error variance, that's better if it works. And the only way to see if it works is just to try to interpret the data. No numbers, no nothing. And there's a lot of debate about when to use what and when it will work and when not, and these kind of things. And we won't bother about this. The easiest way to go about it is simply try the different things that you can do here. So try principal component analysis and try factor analysis. Very often it doesn't matter so much. Sometimes you get stuck with an item battery where principal components doesn't work, and factor analysis might help you in the right direction. I'll give you an example in a minute. Okay, so how does that work in Stata? This is what we had before, factor, and then all the variables, and then PCF for principal component factors. And the alternative command for, let's say, true factor analysis is this one, factor, and then all the variables, and then PF, or just forget about all the stuff behind the comma altogether, because the default actually is this one. Let's see. Oh, wait a minute. No, I think I had that in the actual PowerPoint. Yes, I did. Okay, so here I'm running a factor analysis, or actually a principal component analysis here, and a factor analysis there, on a couple of different items, all related to people characteristics. Nervous is the first one, being cheerful is the last one, and there are a couple in between. In total there are 12. So this is the output that we are used to from last week. We have the eigenvalues sorted from highest to lowest. We see that a couple of them here, 3, are above 1. So in this case that Kaiser criterion would say there are in all likelihood 3 dimensions here in the data. And here you see something else. Here you see the factor nervous cheerful, but then without the PCF behind it. And now you see again a list of eigenvalues, but there are a couple things different here. Some of which you do not see in this output just yet. First of all, now it's possible that we have negative numbers over there. Here, that could never happen. Lowest would be 0 or slightly above it actually. Here, negative is possible. Here, Stata will by default stick with the number of dimensions that is here 3, representing the number of eigenvalues above 1. Here, what Stata will do is assume that all the factors that you want to retain are the eigenvalues above 0. So this 5 here, the 0.7, the 0.5, the 0.2, and the 0.08 will be retained. If you ask Stata to rotate, you will get something here that assumes that you want 5 dimensions. You will get something there where Stata assumes that you want 3. So you have to make sure to keep that into account. You can change it yourself by adding the number of factors that you want in the actual command. We saw that last week as well, and we'll see it in a minute too. But here you already see that this is slightly different from there. Let's see. Yeah, I don't want to go too much about the number of parameters and the number of factors. The more important thing here is that the number of retained factors here is 5 and there is 3. Okay, there's a paper where you see quite a bit about the decision styles that we talked about in the example. Just want to mention that in the slides that that we have, and indeed we are supposed to find 2 dimensions, and we did. So in our case, it actually worked with our own data as well. Okay, then all the assumptions and sample size stuff. This is normally where in multiple regression you start to sigh already, because there is a long list of things that you have to check, and you know, it's no fun. Here it's easier because it's way more difficult. So we do not have any real solutions to this other than a couple of rules of thumb, and that's pretty much it. So that's good. Here we have it. These are the rules of thumb that you could use for a factor analysis, and well, yeah, basically this is hand waving to a large extent. So here you see a couple. We need 10 to 15 participants per variable, or per item I should say, 5 to 10 participants per variable as long as the sample size is relatively small. Above that it doesn't matter anymore. Or 100 cases is poor, 300 is good, and 1,000 is excellent. Or even more complicated, or slightly more complicated, based on the sample size and the magnitude of the factor loading. So the 0.7s and the 0.8s and so on that we had before. If a factor has 4 or more loadings larger than 0.6, you're home free, no matter what. If a factor has 10 or more loadings larger than 0.4, you're okay if the sample size is large enough, where large enough is above 150. Or if you have factors with just a few low loadings, start to worry. It's only okay if your sample size is relatively big, above 300. And one of the reasons, by the way, why this is the only thing we have, try to think back about these sample size things that we did before. You had to start with, okay, if I have, for a t-test, 2 groups that are normally distributed, and then let's see how many cases that I need. Well, you have to assume something about these groups, about these normal distributions, and then try to figure out what should happen. Here, if you have 10 of these items, and you have to assume up front something about the extent to which all these 10 items correlate with each other, because that is what is going to determine if you find dimensions. Yeah, normally you do not know up front for these 10 items that you have what the expected correlation between all these things is. So it's not so obvious to do something that makes sense here. And all this is based on, yeah, let's give it a try, run a few simulation studies, and then we hope for the best, basically. Then so sample size is easy. One thing to remember would be if you're using a data set above 500, then usually you are fine. Underlying assumptions here. Well, it's all based on correlation coefficients. We started with, well, let's look at the correlation coefficients, and if the matrix of correlation coefficients looks like this, here they are all high, and there they are all high, and here they are relatively low, then we have a pretty good idea where the dimensions are. But given that it's all about correlation coefficients, we need interval level variables, otherwise there are no correlation coefficients. And already this is problematic because, well, all these item batteries, usually they have 5-point scales or perhaps 7-point scales, but yeah, that's not really interval. Nevertheless, it has become more or less standard to all close our eyes for that and just pretend as if 5-point scales are interval scaled as well. And the idea is that if you have enough of them and enough cases, then the nastiness will cancel out, we hope. Then actually also what you need is normally distributed variables. Well, you also know, of course, that this cannot be right. If we have items that have 5 different values, that this is not going to be coming from a normal distribution. And obviously, you need substantial correlations among the variables. We're trying to measure something here with a set of different items. So if there are no correlations there, then apparently you're not measuring the same thing with all these different items. So that's relatively obvious. So this implies that this is one of the few cases where we know that all the things that we do here, all the factor analyses that we're going to run, in principle are wrong, because all the basic assumptions are not really met, but that we hope that it's good enough. So in that sense, it's all easier here because it is more complicated. We do not know how to solve it any other way, so we just do it. Okay, then let's suppose that you need to create one, because this can typically happen. You want to run an experiment or a survey. Okay, this we covered before. Check for somebody else who did the work. This is not only good practice because it gives you less work, but also because if somebody else has tested an item battery and knows this is in principle working, then you do not have to do it. And we know that you have a measurement thing that'll work. And here you see what you need to do in more detail than I mentioned it last week. You create a large list of items, more than 20, you run a pilot with a batch of people, 25 or so, and you check. You'll find that some of these items are incompatible with the rest. Well, how do you find this? If you look at what the dimensions are, they never load on any kind of dimension. So apparently they do not fit very well. Or all the time they load on all the dimensions. That is also something you don't want. You get rid of these. Then you want to measure reliability, for instance, by measuring the same thing twice on one person, let's say with a week in between. What I don't want is that I'm measuring a characteristic here that depends quite a bit on, let's say, the day of the week on which I ask you. So you want to have some reliability here, a reasonable guess about that in principle is measurable again and again and will give a decent retest values. Then you want to measure, of course, something about validity. You say, okay, I think I'm measuring happiness here. It would be nice to have at least an extra check before you go and do it, that this is indeed happiness. So you want, for instance, correlations with external measurements of happiness, if that's the thing you want to do. And you see this coming. This is a lot of work. So this is also a reason why you want to have this, right? It would be nice if somebody else has done all the work for you. And then, what happens quite a bit is then you find out, this is an excellent item battery consisting of 27 items, but that creates a survey that's way too long, so I have to make sure that I already bring these 27 back to fewer, because even though these 27 might be fine, if I put that in a survey that I put online somewhere, then too many people are not going to answer all these kind of questions. You look at where the item loadings are highest. These apparently are the strongest items. These you keep, and you get rid of the ones that fit the worst, relatively speaking. Yeah, this is important to realize here, that this is one of the, well, perhaps not even one of the few, but this is at least an example of where the statistics part is there, but let's say the hand-waving part and the interpretability of the data and knowing something about what it is that you're measuring is actually crucial, because you have to decide at some point, yeah, now I see this set of items here is a dimension and it represents this, and for that you simply have to be able to read the questions and see what these different items represent. And here you see, well, principal components versus factor analysis, the number of factors to retain, you think 3, I think perhaps 4, the kind of rotation that we use. And then, yeah, until the maximum amount of reasonable interpretability is reached, whenever that happens, it's not really clear. So many of these examples are actually easier if you know what you're supposed to find. The big 5, as we have it in our own data, there you know for each and every item, this one is supposed to load on that dimension. This one is supposed to load there. You can simply check and see if it works and get rid of the ones that do not work. Okay, so now what you need to do, given that in a minute we also know how factor analysis works, and I'll show you an example. But this simply means that we have an extra degree of freedom to try to make sense of our data. So we already had degrees of freedom when we had the principal components analysis. Now we have another one, namely simply use factor analysis instead of principal components, and use that especially if your principal components doesn't work so well. And there are quite a few of these examples where it doesn't work so well. Okay, so you start with this. First, a principal component analysis and a factor analysis. Then get rid of any items based on KMO. It may very well be that that KMO value that says something about, okay, is factor analysis reasonable here at all, suggests in that list of 20 items that you have, there are a couple that do not fit very well in the rest. And if they are really, really bad, it might even be that the total KMO value is really low because these bad ones are actually in there. What you do is you get rid of the bad ones, you rerun the whole factor analysis, you check again how high is the KMO value now. If it's high enough, you're good to go for the rest. Then you start rotating. Oh, and for ease of, actually I forgot one step in between. You look at the results, obviously, of your principal component analysis, and one of the results there at first will be how many dimensions do you think there are. You rotate using Promax first, and then you try to figure out, okay, what are the dimensions here? And you try to figure out what are the labels for the different dimensions. This is the part where you need to run and rerun, try again, try it once with 3 dimensions, once with 4. Is it now working? I think this is this and that's it. Okay, at some point you think, okay, 3 dimensions, that's the closest to something that makes sense here. If you've rotated with Promax, you're assuming that there can be a correlation between the different dimensions. Double check if that's really there. If it's not there, if the factors do not correlate much, and we saw this last time, rewrote the whole thing, and now do not do this with Promax anymore, but use Varimax. That thing will actually make sure that there is no correlation between the dimensions, and that will help in the sense that Varimax is better at creating weights for the different items that are more extreme. So the lower values will go closer to 0, the larger values will be further away from 0, and all that is good for interpretation. Okay, now you see, hopefully, that if indeed they didn't correlate so much, that Varimax will help you interpret the whole thing even more. If you do not have this, then you're stuck with these. And in the end, you create new variables in different ways, and you double check that the different ways in which you create the variables doesn't matter so much. If they do, panic. Okay, then you're done. Now you know, okay, my set of 40 items indeed fits very well on the 5 personality dimensions that I expected. It's, these. There are a couple of items in there that do not fit very well. Let's throw them out. And then I have 5 new variables left for each and every participant in my data. And all the subsequent analyses are going to be used using these 5 variables and not the separate items anymore. Yeah, so more than ever, you see here that your answer is a story about the data, what's going on there, and not just a big bunch of code, and then you're just done. You have to explain what it is that you're doing. So let's see how that works in practice. I stopped here where I calculated the different factors here in A, B, and C ways. Now here I start with factor analysis. Let's see, all this over there, in this case on the same Q9 questions, but now running a factor analysis. Let me get rid of the plots here. There. So this is the first output that we get. Remember we had 2 dimensions here. Let's see, a 3, a 1.27, but also a 0.27 and a 0.1. So here the number of retained factors is actually 4 when we run a factor analysis. That KMO value says, well, 0.8, and all these are pretty decent as well, so there is no reason to get rid of any of the items here. Here I rotate. Well, here you see what you normally do not want to see. Actually, I wanted to retain here only 2 dimensions, but because this factor analysis sticks to a different interpretation, we now have 4. I don't want that. So now all the rotation stuff, if I don't do anything about it, will be like this. And luckily here it doesn't matter so much, because here if I get rid of all the weights of the different items below 0.3, I see that dimension number 3 and dimension number 4 simply do not exist anymore, with, well, one exception, and that is this item over there. So here I need not even bother correcting that Stata is only using 2 dimensions, because here I find, yeah, right, we get the same thing again. These first 5 again are connected together, and the second set of 5 are connected. This is nothing over here, because there is not a single weight that is above 0.3, and this is, well, also nothing, because there is only this one over there. I'm looking here at the common variance in the different factors. I rotated using Promax, so here I can get numbers that are away from 0, and I do get numbers that are away from 0. Especially here for between 1 and 2, it's minus 0.37. So there indeed is correlation between the dimensions. I'll stick to rotating using Promax. And here you see that I try the same thing now with 3 factors. So I superimpose that, even though I know now that Stata will stick with 4, I want to make sure that Stata sticks with 3. In this example, I use 2. I know that that will be the answer in the end, so let's have a look at that one. And here you see once again, okay, first, where are we? There. Again, these same numbers, that doesn't differ, but what is now retained is only 2 factors, because I made sure that Stata will stick with only 2. And after a rotation, leaving the ones with 0.3 out, I get indeed these numbers over there again, and these over there too. That 0.38 is still there, and we're good to go. So again, here we find this example is very clean cut, more clean than you get it normally. Doesn't matter so much. Principal component analysis, factor analysis. Again, you find 2 dimensions, the first 5 on one, the second 5 on the other. Okay, just to show you that it's not always that easy, here we have another set of questions. That's Q8. Q8 was all about I can work efficiently at any time of the day. So if you're a morning person or an evening person, or how energetic you are. So let's see what happens there. This is just a principal components analysis again. And let's see what we have there. Okay, let's first have a look at the at the Fapara plot again. 2 dimensions here. one big one over there, one big one over there. The rest is all beneath the dashed line. So this suggests, well, this Fapara plot says there are two. I can immediately look at what the Kaiser criterion would say, because these are the eigenvalues. This is above 1, this is above 1, this is also above 1, this one also, and this is also perhaps. So if I use that criterion, then I would get 5, which is quite a bit more. And if I use the scree plot criterion, okay, where's the elbow? It's over there. Then I would get 2 or 3. So now I have 3 ways to think about how many dimensions there are. One says 2, that's looking at the plot here. One says 2 or 3, that's the elbow plot argument, and one says it may be 5, that's the Kaiser criterion. So anything between 2 and 5 might be decent here. So let's see, what did we do there? Okay. So first here. 5 dimensions are retained, and here you see the different values with the 0.3s excluded. Okay, and now the tedious work begins. I'm looking at the Q8 questions over here, trying to figure out what these dimensions might be. The first thing to do is look at, are there any items here that load on more than one dimension? If yes, not a good thing. So there is one over there. This one is in dimension number 3 and in number 1. This one is in 1 and 2, this one's in 2 and 4, and these are both in 4 and 5. Okay, so I don't like it much, but perhaps not that detrimental just yet. But let's give it a go, and first try to figure out, look at the largest weights here, what the different dimensions might be. Okay, 0.8 for number 2. What was number 2? I feel I can think best in the morning. Try to find another one. Number 5. If I were to study anything by myself, I would rather do it in the evening. Okay, that makes sense. So if this is being a morning person, then it's not so weird that this one is positive and this one is negative. Number 9, my work goes better in the afternoon. Okay, so if you're a morning person, then it's not likely that you score high on that. So I understand that this is a negative. Number 13. I am in my best form in the morning. Okay, so now I'm starting to believe that indeed this is all about the extent to which you are a morning person, period. Now the second one, let's see, highest number is there. That's number 12, and we do not see number 12 in any of the other dimensions, which is good. If I need it, I'm able to, wait a minute, there, to concentrate at any time of the day, okay. Number 8. It's there, I can focus at any time of the day. Okay, so I'm starting to believe here, this is all about the extent to which you can focus throughout the day anyhow, so not so much morning person or evening person and just can do this all day. Then still could be that you score high on dimension number 1 and 2, so I am more of a morning person, but nevertheless, let's say good enough to maintain my focus all day. So I'm doing quite well here. I have an argument what this might be, and I also have an argument what that might be. Morning person, the extent to which I can focus throughout the day. And now it gets probably more complicated. Let's see. Factor number 3, that's 8, 6. This one, my mood stays the same throughout the day. Okay, so that's not so much about energy, but yeah, let's say how well you feel. 11, what is 11? I am usually in an excellent mood in the morning. Okay, so this, I already don't like this now, because the first one was about the whole day, and the second one is about only the morning. And 16, what's that? I feel sluggish in the morning, and I warm up slowly during the day. This is not about mood at all. So, this is more difficult to determine what might that be, given that I have these 2 dimensions there already. And if you check what you get for 4 and 5, you'll see that is again, not very clear what it exactly might be. So if I have no story for 3, 4, and 5, even though I have a decent story for 1 and 2, you have to try something else. Give it another go with a different way of rotating. So here, for instance, I'm trying to stick to 3 factors instead of the 5 that Stata originally used. Try the same thing. I get that plot a couple times. Now I get 3 dimensions with Also not something that's very nice. I get now 8, 7 that loads on 3 dimensions. I don't want that. This one also loading on 2 and not very high. Okay, so perhaps it makes sense to get rid of number 10 and get rid of number 7, and then try again to see if now these dimensions make sense. And the difficult part will be what that third dimension is, because the first two, in all likelihood, are working very well, but the third one is not. Well, I'm going to cut it short here, because there are different ways to do this. Try 2 dimensions, see if it works. Try 3, but do not use principal components, but principal factors, so factor analysis instead of principal component analysis. And in the end, what you're hoping to find at some point is, okay, now I'm more or less converged, and I converged to, let's say 2 dimensions here. I hope, because I think the original item battery was meant to measure only 2, if I remember correctly. But if that doesn't happen, then it doesn't, and then you may find 3, or you may find nothing. And yeah, you simply have to go through the possibilities that you have and see how it works out. Any questions about this part? Besides that you see coming that especially for larger item batteries that are a little bit more vaguely measured, this can take a while before you converge mentally to what in all likelihood this is going to be. Okay, couple leftovers, not related to this data part, because in principle this completes the factor analysis part, and with the multi-level and the logistic regression and the Stata stuff, that is what you need to know for the exam.